So now we turn to a discussion of how the states of the hydrogen atom resemble those of multi-electron atoms and how they can be used as a model for all of the elements. The common point is that the arguments that led us to choose the principal quantum number associated with R, the azimuthal quantum number associated with the total angular momentum squared of the atom, and the magnetic quantum number associated with the angular momentum around one axis, are based on the fact that the Coulomb potential is a central potential. They're based purely on symmetry arguments. So long as we can regard the atom as a cluster of positive charge around which an outermost electron orbits, this picture will still hold. Now, it's clearly not completely accurate, but to a first approximation, it's a good starting point. So here is an electron, outermost electron involved in the chemistry of the atom, and then here is a shell of all the other electrons, all containing negative charge. And then in the middle, a nucleus containing Z, where Z is the atomic number, positive charges. So here we have Z minus 1, negative charges, and out here the negative charge associated with the outermost electron. So in this picture then, this still looks just like a Coulomb interaction between a positively charged or a negatively charged electron and an effective nucleus with a charge of just 1. Now this Z effective is not actually 1. We saw that the wave function of the electron does penetrate into the innermost part of the atom. So just to remind you, if we plot the probability of finding an electron versus radius, then, for example, for the 3s state, it looks something like this. So although most of the probability density is found on the outside of the atom, these parts of the probability density overlap with other electrons and cause the effective to be not equal to 1. However, if we take this simple picture and recognize that because interactions between electrons will carry with them an energy penalty, and therefore the various angular momentum states which were degenerate in the hydrogen atom, that is to say only the principal quantum number determined the eigenenergy of the hydrogen atom, in the case of many electron atoms we will have to recognize that now the energy must depend on the angular momentum states, because these determine the shape of the wave functions and how the electrons interact with electrons inside the inner core of the atom. However, with all of these qualifications, we can at least use the excited states of the hydrogen atom, the various states for which L and M are not equal to 0, and the states greater than n equal 1, as models of the states that will be filled when we add extra electrons and extra protons to make multi-electron atoms. So with this in mind then, let's build up a table of what would happen to our states as we add one electron and one proton to the hydrogen atom to move through the periodic table. So to remind you, the principal quantum number n can be any integer. The azimuthal quantum number is an integer that is restricted to a range of 0 and n minus 1. And the magnetic quantum number lies between minus L and plus L. So here is a table showing what happens as we fill up these orbits. Now this table, of course, is correct for the hydrogen atom. In a multi-electron atom, we will be adding one proton and one electron at a time to fill up these states in the order of their energy, from the lowest energy to the highest energy. We'll see that electron-electron interactions throw in some wrinkles, but let's run through the states. So begin with the quantum number n equals 1. So for n equals 1, we see from these rules that I've listed on the whiteboard at the right that there is no choice for L, so L is condemned to be 0 as M must be. So that, of course, is the hydrogen atom. It has one orbital in the subshell. This is the 1s orbital. So let's write this notation down. And because of the exclusion principle, it can hold two electrons, one spin up and one spin down. So this would be the occupancy for hydrogen. For helium, we would add a proton, so we keep the effective nuclear charge still equal to 1, and one more electron spin down, and that would complete the occupation of the 1s orbital. Now let's go to the principal quantum number equal to 2. In this case, you can see that n-1 is 1, so L can have the values 0 or 1. Starting with 0, we have the 2s orbital, so let's write this out now. And like the 1s orbital, it can have one electron in it or two electrons in it. We'll walk through the periodic table in the next lecture topic. We have m equal to -1, 0 or +1 for L equal 1. So these are the three m quantum number states corresponding to the total angular momentum squared eigenvalue of 1. So now we have three m orbitals, and we can put up to 6 electrons in these, spin up and spin down paired. So this means that in the corresponding to principal quantum number of 2, we can put 2 electrons into the 2s state, and then into what is called the 2p state, corresponding to the principal quantum number being 2 and the azimuthal quantum number being 1, we can put a further 6 electrons. So this allows us then to put a total of 8 electrons into the orbitals associated with the principal quantum number 2. So now we step on to the principal quantum number 3. This then allows us, once again, a 3s state into which we can put 2 electrons. For L equal 1, we have the 3m states again, -1, 0, and +1, into which we can put a total of 6 electrons. So now that's already our 8 electrons. However, we are now allowed to have L equal 2, because it can run between n-1 and 0. For L equal 2, we now have 5 states associated with the magnetic quantum number, -2, -1, 0, +1, and +2. This is then an additional 10 electrons that can fit into these d states. So the total number of electrons that will fit into the orbitals corresponding to a principal quantum number of 3 are 18. So we can continue this process. Just a comment that when the azimuthal quantum number goes to 3, one then has a possibility of m quantum numbers -3, -2, -1, 0, +1, +2, and +3. And so in this total now of 7 m states, one can put 14 electrons. These orbitals are called the f orbitals. So this notation, s, p, d, and f, is used in describing atomic orbitals, and we'll turn to this when we begin our review of the periodic table in the next module.